Now, in the chapters over charges and capacitors, one of the issues that we have with those kinds of things, I talked about, you can have this much charge, etc., but we can't really count the number of charges. There are too many. However, what we can do is that we can measure how rapidly those charges move. Okay, they create magnetic fields, which we can then set up equipment that allows us to measure that. And as a result, we have something else, not just the charges, but we have something called the current. The symbol for current is I guess because they already used up C on capacitor. Current is I, and what current is it is the change in the number of charges traveling at a given moment in time, or over a period of time. Okay, and for those of you who are calculus related, as you take the limit as that delta t shrinks down to 0, this is dq dt. Okay. But that's the current, and the units of current, well, right here we have coulombs, and of course time is in seconds. Coulombs per second, that's the unit of coulombs of, that's called an ampere. Okay, that is what current is measured in as amperes, and usually that's just shortened and written as amps. Okay, now for instance, if we were able to measure and we knew that we had 100 coulombs of charge that flowed through a particular wire in 80 seconds. So, well, what is the current there? We would say, well, 100 coulombs divided by 80 seconds. That's 10 over 8, which is 5 over 4, which is 1.25 amps would then be what we would get there. Okay. Now, we could think about like, well, how many electrons is that, etc. But again, that's a more difficult thing to talk about. The number of coulombs is a reasonable measurement here. If we talk about, like, there's 1.6 times 10 to the minus 19 coulombs is the charge one electron has. So this is somewhere in the neighborhood of 10 to the 19 or 10 to the 20th electrons that are moving in order to create that kind of current right there. Now, let me erase this. Talk about how we measure current. For current, we have devices that measure these things. When I did the capacitive lab, we had a capacitance meter. Okay, we also have voltmeters. We have voltmeters and we have ammeters. And basically, if you think about a circuit, it could be, you know, flowing up to whatever, just flowing up to a lamp or whatever, coming back down. We've got a battery here, and of course there would be current flowing through this circuit and around here. And that is those charges that are coming out of there and trying to get over to the negative side of the battery. And when we measure these things, there's a couple different devices we use. We use what's called a voltmeter. And a voltmeter, we would take and we connect across the voltage. So we put a voltmeter on one side of the battery, the other side of the battery, or anywhere in that line, and we could measure what the voltage of the battery is. That is a connection where the wires that come from the voltmeter, one of them goes on one side of whatever you're trying to measure, and the other one goes on the other side. The way we measure current is a little bit different. The way we measure current is what's called an ammeter. And when we have an ammeter, it has to be, in order to measure the current, it has to be a very, very low resistance device. And as a result, if we were trying to measure the current between here and here and put an ammeter like this, the fact that the ammeter is going to be higher resistance than this wire here, no current would flow through the ammeter. It wouldn't measure what's going on in this wire. It would measure only what's flowing through the ammeter. So we don't do it like that. In order to measure with an ammeter, to measure the current, we put the ammeter right in this line. So not like voltage, where voltage is across the whatever you're trying to measure. Here we put it right in that line. We have to force whatever current there is has to flow through the ammeter in order for us to measure that. Okay. And it turns out that how rapidly things fly through here depends on what types of materials we have to run through here. And different materials have what we call different resistances. Okay, if you think about this, current flows very well in copper, flows very well in aluminum, flows very well in gold and a variety of other things. And other things doesn't flow so well, and doesn't flow very well in iron, doesn't flow very well in molybdenum, various other metals. So as a result, what we do is we make most of our wiring out of copper. Copper's cheap and has very good properties as far as current flowing. There are metals that are better, but they're more expensive. So we make most of the things out of copper. However, when we want to resist the flow of current, what we do is we put in here something that will resist that, called a resistor, and we make that resistor out of different materials. Now the symbol for resistor just looks like this. And if you think about that, it just looks like, wow, the current was flowing along here nice and smoothly and didn't run into any barriers. Then it got here and has to go up and down mountains in order to get through here. So that slows it down. That's a resistor. It resists the flow of current. Okay? And all we have to do in order to do that, we could build something that actually went back and forth like this, and it would be harder to flow through more wire than to flow through less wire like it does here, straight through. But what realistically is done is this is made out of something like iron, which is also cheap, but has poor conductive qualities, and as a result, it takes longer to flow through that resistor. And what will end up happening is that most of the voltage, so the voltage is basically how hard this, if something's 12 volts, that's how hard it's trying to push charges through there. Most of the work would be done pushing from here to here. Flowing from here to here in a copper wire doesn't take much push at all from the battery. But to get through here takes the push, and that's where we end up getting the using up the voltage there. And it turns out that the way these things are related, voltage is equal to the current multiplied times the resistance. This is what's known as Ohm's law. And so basically that gives us that relationship between voltage, current, and resistance. And if we measure both the voltage and the current, then clearly we can divide by I here and say, well, then we can measure what the resistance is, and that's what I'll do when I do lab. And we can get these different resistors. Resistors are dirt cheap, and you can buy one, and it'll say on it what it is. This is a 100 ohm resistor, or that's a symbol for ohms, okay? 100 ohm resistor, you could have a 1,000 ohm resistor, all the way up, they have like mega ohm resistors, which would be millions of ohms. So there's a wide variety of different resistors you can get, and they're just little tiny guys, and very cheap, and so very easy to do labs like this, inexpensive. So, and again, to just do a quick example here, if we had a 12 volt battery, and if we had a resistor, let's say that our resistor we knew to be a 100 ohm resistor, then we would say, okay, based on Ohm's law, V divided by R is equal to I. We could calculate what the current should be. That would be 12 over 100, which is 0.12. That would be 0.12 amps would be and frequently current in this range is what we often see, and we often talk about it as milliamps, okay? Even though we could have resistances of like a value of 1 or whatever, typically resistance is in hundreds to thousands to millions of ohms, and as a result, for reasonable voltages, we could have super high voltage, we could have lots of current, but usually we have reasonable voltages like this, we have milliamps worth of current. And of course, the more current there is, then the more pressure that puts, pressure is not quite the right word, but the more strain it puts on these wires because they will heat up. What's going on here is in order for a lot of current to flow, this is just basically a pathway for this current. Lots and lots and lots of charges have to fly. Well, if you've got a very, very small wire as opposed to a big wire, there's just a smaller road, and this wire will heat up as current flows through it. And so really, really tiny wires can't handle amps worth of current, but pretty much anything can handle a few hundred milliamps. Brings me to power that is consumed in a wire, what is equal to current times the voltage. So the product of those two, as the current goes up, then the power that's used is going to go up as well. And then that is what is going to heat up that wire in the process. Now Ohm's law, this idea right here, does not work for all materials. As I mentioned, some things work better than others, but some materials it doesn't work at all. These have to be conductive materials, what typically are classified as being ohmic materials, meaning that they follow Ohm's law basically. But if they follow Ohm's law, they have some resistance based on the type of material they are, and also based on how big they are, how long, how wide the conductor is, etc. And turns out that the resistance, this is row, this is called resistivity. So the resistance depends on three things: the resistivity of the material you're using, the length of the wire that you have, and the cross-sectional area of the wire. So a thick wire would have more area, therefore its resistance would be less, because again, you got a big thick wire, it's easier for the charge to flow through there, not as much resistance. This is the length, how long do we have to go along this, resistive path, and then this is the resistivity, which is material specific and will be different if it's copper or aluminum or steel or carbon or whatever else you may have in there. And of course there's tables that have resistivity. We can't just say, well, we've got a wire, it's going to have a resistance of this because it's steel. No, we would have to know what the resistivity of the metal is in there, but also how long is the wire and what's the area of that wire in order to calculate the resistance itself.